Assalamu alaikum everyone. My name is Adeem Aslam and I welcome you all to this first lecture on analog and digital electronic circuits. Before I start, I would like to draw your attention to the fact that I have uploaded the course outline, which contains details on the content that we are going to cover in this course. The course content is arranged not only lecture-wise but also week-wise, and I have also mentioned article numbers from the textbook for the contents that I cover in each lecture. As far as the textbook is concerned, I will be following the book titled Microelectronic Circuits by Adele Cedra and Kenneth Smith. I'll be following its 6th edition. Although I believe 7th edition is also available and there is not much difference between the two, but I recommend that you follow the 6th edition because I'll be following the 6th edition. I've also mentioned a couple of reference books, one of which is titled Fundamentals of Microelectronics by Behzad Razavi, which is another very good book. So I highly recommend that you get this reference book as well. So as the name suggests, analog and digital electronic circuits is the study of electronic circuits which analyze and process analog and digital signals. But prior to understanding the working of such circuits, I think it is imperative that we understand the signals themselves. So as shown in this outline for this lecture here, I naturally wanted to begin with a discussion on signals. So I'll discuss some types of signals, their different representations. I'll define analog signals, and I will go through the process of quantization to obtain digital signals. In the second part of this lecture, I will talk about amplifier, which is perhaps the most often used electronic circuit, especially in analog electronics. I will not discuss the internal circuit of the amplifier. I will only discuss the external characteristics of an amplifier. It will be a brief introduction to the amplifier circuit. So we know signals as functions which contain useful information about some physical system. An example is an acoustic signal, which contains useful information for a listener. Physical signals of this form cannot be directly passed on to the electronic circuits for analysis and processing, obviously. So they, first of all, need to be converted into electrical signals. This conversion of physical signals into electrical signals is achieved through what are called as transducers. So a common example of a transducer is a microphone that I'm using, in fact, right now, which converts speech or acoustic signals into electrical signals. So in the study of electronic signals, we will limit ourselves to electrical signals only. We won't be concerned with physical signals and their conversion through transducers. Furthermore, for low-frequency electronic circuits, time-varying signals will be considered. So the electrical signals that we will encounter in this course will be time-varying electrical quantities. There are two types of such electrical signals, namely the voltage signal and the current signal. This figure on the left here shows a voltage source model. This is the model for a source of voltage signal. And this on the right here shows a model for the source of the current signal. The resistor RS on the left models the dependence of the voltage source Vs on the current drawn through it by the load, which would be connected here in between these two terminals. Whereas this resistor RS, this shunt resistor RS, it models the dependence of the current source IF on the terminal voltage, which is again defined by the load, which will be connected between these two terminals. So if the voltage source Vs and the current source Is, they follow this relation, then the two circuit models are actually equivalent and can be obtained from one another. For example, this voltage source model here can be obtained from this circuit through the use of Thevenin's theorem, whereas the current source model here can be obtained from this circuit on the left through the use of Norton's theorem. Electrical signals can be classified as aperiodic, which are defined over finite time interval, and periodic. Periodic signals repeat with time, hence the name periodic. So an example of a periodic time domain signal is a sinusoidal voltage signal or a sine wave voltage signal, which is mathematically given by this expression, in which Vp is called the peak amplitude. It is represented in volts. Omega naught, given by 2 pi over capital T, is called the angular frequency, where the capital T is called the time period. And we have assumed that the phase of the signal is zero. There is no additional term within the parentheses. Otherwise, we would take that non-zero phase into account as well. Inverse of the time period is called the frequency, as can be seen from this relation, and is denoted by F. So if the time period is expressed in seconds, then frequency is defined in hertz, where 1 hertz equals 1 cycle per second. Furthermore, we see that sinusoidal signal, which has zero average or DC value, it is also called an AC signal. So this is an AC signal. This figure shows an example, an illustration, in fact, of a sinusoidal signal for which the peak amplitude is set to 2 volts and the frequency is set to 50 hertz. So periodic signals can either be represented in time domain like this, which is time, or they can have representation in the frequency domain. So frequency domain representation is enabled by the fact that every time domain signal can be expressed as the following weighted expansion. This is also called the Fourier series expansion. This in which E represents the exponential function, I represents the iota, and the weights Ck, which are given by this integral, they constitute the frequency domain representation of the signal Vt and are called as spectral coefficients of Vt. So can be observed from this expansion here in equation 2 that any signal Vt can be expressed as a weighted sum of sinusoidal signals. So if we use the Euler's formula and replace exponential with this form, where cosine is actually a sine signal, only displaced in time, then we can see that any signal Vt can be expressed as a weighted sum of sinusoidal signals, where the coefficients or the weights Ck are obtained by finding this integral over time, in which this capital T here refers to the time period of the signal Vt. So in the study of electronic circuits, we'll be only concerned with sinusoidal signals, because for all the other arbitrarily shaped signals, we can use this expression here in 2 to represent them as weighted expansion of sinusoidal signal, which means that if we have a result for a sinusoidal signal, then it can be mapped through this expansion to an arbitrarily shaped signal Vt. So we'll be only concerned with the sinusoidal signal. As an example, here I show a symmetrical square wave signal. It's also called a bipolar square wave signal, which is defined by this expression, in which it takes a constant Vp amplitude over 1/2 of the period and a constant minus Vp amplitude over the next half of the period. So here VP is set to 2, so it is 2 over the first half of the period and minus 2 over the second half of the period, and then it will just keeps on repeating itself. So it's a periodic signal with a frequency of 50 Hertz. So we can find the Fourier representation of this signal by solving the integral. Since it takes on two values, Vp and minus Vp, I have divided the integral into two halves. And it's a fairly simple integral to solve. So it results in this expression shown in the third equality. Now this expression can further be simplified by first of all noting that omega naught t by the definition of omega naught is equal to 2 pi. So if I replace omega naught t with 2 pi, I'll have exponential of minus iota 2 pi k, which can be seen from the Euler's expansion to be equal to 1. I'll have minus 1 here, I'll have a minus 2 here. So furthermore, this is the same term as this, so I'll have twice this exponential term, in which again, if I replace omega naught t with 2 pi, 2 will get cancelled with 2. I'll be left with 2 times exponential of minus iota pi k. Exponential of minus iota pi k, again from Euler's formula, can be seen to be equal to minus 1 power k. So I'll have 2 times minus 1 power k minus 2. That this factor of 2 can be taken outside, and this denominator, in this denominator, again, I can replace omega naught t with 2 pi. So the 2 will get cancelled with 2, and I'll be left with this expression, which can be seen to be equal to 0 for even k, because for even k, this will be equal to 1, and this term will sum to 0. So Ck will be non-zero for all values of k, for which they are given by this expression. Because for all values of k, this is minus 1, so minus 1, minus 1, minus 2, minus 2 iota Vp over pi k. Now using the Fourier expansion of the signals, I replace Ck in the summation, and I replace in the expansion, sorry, and I replace the complex exponential with its Euler's using Euler's formula through with this expression. So this expression can be simplified by observing that the coefficient of the cosine term for positive value of k will get cancelled with the coefficient of the cosine term at negative value of k. So cosine terms will have no contribution. Similarly, the coefficient of the sine term at positive value of k will have the same signature and magnitude, same value and same signature as the coefficient of the sine term at negative values of k. So instead of performing the summation over positive and negative odd values of k, I can perform the summation over positive odd values of k, and then multiply the coefficients by a factor of 2, because they correspond, they have the same value for positive and negative values of k. So it's a simple arithmetic, and I'm sure that everyone, after a couple of mathematical steps, can verify that this is the final form of this Fourier expansion for the square wave signal. So expanding the summation and taking this factor 4 Vp over pi out as common, I can write the square wave Fourier expansion like this, in which the first term can be seen to be given by omega naught, which is called the fundamental component. So in this context, omega naught is called the fundamental angular frequency. And all the other terms, they are given by the multiples of omega naught. So this depends on 3 omega naught, 5 omega naught, 7 omega naught, and so on and so forth. So all of these higher order terms, they're called harmonics. So this is the third order harmonic, fifth order harmonic, this is the seventh order harmonic, and so on. So here I plot the magnitude of the Fourier coefficients versus k. For positive values of k, I have chosen to plot the coefficients for positive values of k, and for k up to 100 because they go down in magnitude with k because they are inversely proportional to k. So the magnitude dies out after a certain k value. So this plot actually shows the frequency domain representation or the Fourier representation of the periodic signal. Periodic signals can further be divided into four categories: continuous time, continuous amplitude signals, discrete time, continuous amplitude signals, continuous time, discrete amplitude signals, and discrete time, discrete amplitude signals. Out of these, the first two, continuous time, continuous amplitude, and discrete time, continuous amplitude signals, they are called analog signals. Why? Because their amplitude varies continuously um, with time. So continuous amplitude signals can have arbitrary values of amplitude which vary continuously with time. Such signals are called analog signals. I mean, the signals whose amplitude domain has continuous variations, they're called analog signals. So here I show two different types of analog signals. This is on the left is a continuous time, continuous amplitude signal. So it is defined at all times, and it is also varying continuously in the amplitude domain. On the right is shown the sampled version of this signal. So I take samples of this signal on the left at discrete times, and I get this signal. So this is a discrete time, but still continuous amplitude signal because the amplitude of the sample is still varying continuously in this range from 0 to 2 and back to 0. So the value of the sample, the amplitude, I'm sorry, the amplitude of the sample depends upon the sample value. So, but it's still varying continuously with time. So this is, although it looks, it is discrete in fact, but it is still an analog signal. It, do not get confused with the samples in the time domain. It is still an analog signal because its amplitude is varying continuously with time. So on the other hand, discrete time and discrete amplitude signals can only have finite set of values in the amplitude domain, and such signals are called digital signals. Digital signals are obtained from the analog signals through the process of quantization, in which the amplitude domain of a digital signal, um, I'm sorry, the amplitude domain of an analog signal is sampled to get a digital signal through the process of quantization. So before I go on to explain the quantization error, let me give an illustration. So here on the left, I show a signal in blue, which is continuous time and continuous domain. So it is a signal, it is a sinusoidal signal given by this expression, and I have only shown the first half of its cycle. So it is half sine wave. So it varies from 0 to 2 in the amplitude domain. So in this particular example, I have decided to divide the range of the amplitude range from 0 to 2 into 4 levels: 0, this level, and then 2. Right? So these are called quantization levels. And this gap here, this step, is called the quantization step. So the analog signals are mapped to these quantized levels as follows. So all of the amplitude, all of the analog values uh, which lie within the lower half of this quantization step, they are mapped to 0. All those values which lie within the upper half of this quantization step, they are mapped to this level. Similarly, considering this quantization step, all those values of the on the analog curve which lie within the lower half, they are mapped to this level. And all those values which lie in the upper half of this quantization bin or quantization step, they are mapped to this level. So mapping the values, the amplitude, the amplitude values of the analog continuous time continuous amplitude signal results in the results in the quantized signal, which is shown by this magenta curve here. And then sampling of this quantized curve results in the digitization of this analog signal. So this is a digital signal corresponding to this analog signal. And not only is it sampled or discrete in time, it is also discrete in amplitude. So the samples can take on finite values from the amplitude. Those finite levels being 0, this, and this. So this is what has been explained here. The quantization error is actually the difference between any two is defined by the quantization step. Quantization error is defined by the quantization step, which is the difference between any two quantization levels. So the quantized signal, such as this one, this is the quantized signal, is obtained, like I just explained, by mapping the amplitude of the analog signal to the nearest quantization level. This introduces quantization error, the maximum value of which is equal to 1/2 of the quantization step. So for example, considering this quantization step, all of the analog values which lie within the lower half, they are mapped to this level, and those which lie in the upper half, they are mapped to this level. So the maximum difference between the value of an analog signal and the quantization step, and the quantization level is when the amplitude value of the analog signal lies at the midpoint of this quantization step. So when that is the case, the difference between the quantized value and the actual value will define the maximum quantization error. So the maximum quantization error is given by 1/2 of the quantization step, where this V range over LQ minus 1 is the quantization step. LQ is actually the number of levels. So for LQ number of levels, we have LQ minus 1 quantization step. So the length of each quantization step is then given by dividing the range of the amplitude by the number of quantization steps. And that is what I've done. So this is the length of the quantization step, and then I divided by 2, which gives me the maximum quantization level. Here I illustrate the same digitization of the analog signal, but instead of using just 4 levels as before, here I'm using 16 levels. And as you can see that the quantized level, the quantized signal, as well as the resulting digital signal, they look very similar to the actual analog signal. Because of the greater number of quantization levels, smaller number of smaller quantization steps, and then smaller quantization levels. So the quantized levels, which are amplitudes of the digital signal, are specified by the binary digits or the bits. For a quantization scheme with LQ levels, the number of bits required to represent the amplitude of a digital signal, which I denote by NQ, is given by this expression, where this symbol represents the integer ceiling function. So integer ceiling function actually takes the integer to the next smallest integer. So for example, integer ceiling of 4.6 will give me 5, integer ceiling of 5.2 will give me 6, and so on. So this actually shows that if I have 4 quantization levels, then I will actually need 2 bits. So 0, 0, 0, 1, 1, 0, 1, 1 will be my quantization levels, which will be described by 2 bits. Similarly, if I have 16 quantization levels, as in this illustration, then I will need four bits. So these are the 16 quantization levels, and I will need 4 bits to label them. So 0000, 0001, 0010, all the way to 1111. So the number of bits is given by the log base 2 of LQ. But if LQ is not a power of 2, then log base 2 of LQ will not be an integer. And which is why I use the integer ceiling function. Because if LQ is, let's say, 6, then log base 2 of LQ will be greater than 2 but less than 3. But I cannot choose 2 because 2 bits cannot represent 6 levels, but 3 bits can represent 6 levels. So that is why I take the ceiling of the number to get 3. The amplitude of the digital signal is then simply given by this expression. This is nothing but the conversion of binary number to decimal. So 00 will give us 1 for the case of 2 bits. 01 will give us, sorry, 00 will give us 0. 01 will give us 1. 10 will give us 2. 11 will give us 3. Um, and similarly, you can show that this is nothing more than a binary to decimal conversion. So B naught is called the least significant bit, and B in Q minus 1 is called the most significant bit. This sampling and quantization of an analog signal is performed by an electronic circuit which is called the analog to digital converter. So ADCs are actually used to convert analog signals into digital signals through the process of sampling and quantization. So now the second part of the lecture is concerned with the brief introduction of the amplifiers. Amplifiers are, like I said before, perhaps the most commonly employed electronic circuits in analog electronics, which are used to amplify the signal. So amplifiers can be built from discrete components, in which case they're called discrete amplifiers, or they can be built from small-scale electronic components which are housed within an integrated circuit, in which case the amplifiers are called integrated circuit amplifiers. These are the symbols used to denote the amplifier. Amplifier is actually a two-port network. So there is a port on the input side, a couple of terminals on the input side, and then a couple of terminals on the output side representing the output port. So this is a generic symbol of the amplifier, in which the amplifier itself is represented by this triangle. This symbol of amplifier is used when one of the terminals on the input side is connected to one of the terminals on the output side. So when the input and output port have a common terminal between them, then we use this symbol to represent the amplifier. So exciting the amplifier like this, in which Vn is a small voltage signal, In is the corresponding current, V0 is the amplified output signal, I0 is the output current, and RL is the load resistor. A voltage amplifier is supposed to amplify the voltage at the input to give the amplified voltage at the output through this relation. The voltage amplifier amplifies the output voltage, amplifies the input voltage, which appears then as the output voltage, where the amplification factor or the voltage gain is given by the ratio of the output voltage to the input voltage. So if in this circuit the output current is 0, or equivalently if we have an open circuit here, then the corresponding gain is called the open circuit voltage gain, or it is also called the unloaded voltage gain, because there is no load connected when there is an open circuit. And unloaded or open circuit voltage gain, as I'll show later on in one of the later lectures, the unloaded voltage gain is different from the loaded voltage gain. These are called the voltage transfer characteristics of an amplifier. So the plot of the output voltage against the input voltage is called the voltage transfer characteristic of the amplifier. And from these characteristics, we see that the slope of the curve is a constant. So slope of the curve, which is the gain of the amplifier, is actually a constant here. So such amplifiers are called linear amplifiers, and linearity is actually the most sought after property of amplifiers. We want amplifiers to be linear. We want the voltage gain of an amplifier to be a constant, because if the voltage gain of the amplifier is a constant, then the output voltage is just a scaled version of the input voltage. It has similar properties, same shape. It is just scaled by the factor AV, amplified by the factor AV. However, if gain is not constant, if, for example, gain is varying with respect to the input voltage, then the output voltage will have characteristics which will differ from the input voltage. That is undesirable because that manifests itself as distortions in the output signal. So nonlinear amplifiers are not desired. Nonlinear amplifiers, they produce distortion in the output. Another amplifier, which is called the current amplifier, or equivalently the power amplifier, has a small voltage gain but a substantial current gain, which relates the output current, referring to this circuit here. It relates the output current to the input current through this relation, where AI is called the current gain of the amplifier. Again, referring to the same circuit, if the output voltage is zero, if this output voltage is zero, or equivalently there is a short circuit at the output, then the current gain, this current gain, is called the short circuit or unloaded current gain, which again will be shown later on, that this unloaded or short circuit current gain is different from the loaded current gain. Now, from the expressions for the current and voltage gain, we can find out the power gain of an amplifier, which is given by the output power to the input power, and can be seen to be given by the product of the voltage and current gains of the amplifier. Amplifiers require DC voltages for their operation, because the extra power, the extra energy that is required to amplify the source signal is actually delivered by the DC voltage sources. So most of the amplifiers, they operate on dual supply, on two supplies, such as the one shown here. So in this circuit, we have an amplifier which is loaded by the resistor RL, excited by the source Vn, and it is biased by two voltage sources, VCC and VEE. This is the common terminal of the circuit. So the voltage at this node with respect to this node is VCC, which means that this node of the amplifier is at a voltage of VCC with respect to ground. Whereas voltage of this node with respect to this node is VEE, or the voltage of this node with respect to this node is minus VEE. So this node is at a voltage of minus VEE with respect to ground, which is why the current is leaving this node and it is entering this node. So this node is at a positive voltage, this node is at a negative voltage with respect to the common ground. We can write the conservation of energy principle for an amplifier, which equates the total input power with the total output power. So the total input power is the power supplied by the two DC voltage sources, denoted by PDC, plus the power supplied by the input source, denoted by PN. The output power is given by the power which is given to the load, denoted by P load, and the energy which is dissipated, for example, in the form of heat, which is denoted by P dissipated. Efficiency of the amplifier is given by the useful power, which is the power transferred to the load, to the total input power. Since V in is a very small signal, because amplifiers are used to amplify small amplitude signals. Otherwise, what is the use of an amplifier? So typically, V in is a very small amplitude voltage signal. So the corresponding power supplied by the voltage source V in is also very small compared to the power supplied by the DC sources. So the sum of the power supplied by the DC sources and the power supplied by the input source is almost always typically equal to PDC, because this power supplied by the input source is negligibly small compared to the power supplied by the DC source. So one can also find the efficiency of an amplifier through this ratio. This is an equivalent way of representing a dual supply amplifier, in which we just show this voltage is at a this node is at a positive voltage and this node is at a negative voltage with respect to the ground. There are amplifiers which operate on single supply, and as we will learn more about the amplifiers, we'll see that such amplifiers will require, for proper operation, they will require a DC component in the source signal. So the source signal for such amplifiers is no more just an AC signal. It is a mixed signal. It is the combination of an AC signal plus an DC component. So now that we have different types of signals, we have AC signals, we have DC signal, we have a mixed signal. In order to differentiate these signals from one another, I will use, for example, for a DC electrical signal, I will use uppercase symbol with uppercase subscript. For an AC signal, I will use lowercase symbol with lowercase subscript. And for a mixed signal, I will use lowercase symbol with an uppercase subscript. Throughout the course, I will keep on following this convention. Finally, we note that the gain of the amplifier, be it a voltage amplifier or a current amplifier, the voltage gain as well as the current gain and the power gain, they are all just dimensionless quantities, because voltage gain is the ratio of output voltage to input voltage. Current gain is the ratio of output current to input current. Power gain is the ratio of output power to input power. So all of these are dimensionless quantities. So another useful way of representing these dimensionless quantities is in terms of decibel units, or dB for short. So voltage gain represented in dBs is given by this formula. Current gain represented in dBs is given by this formula. And power gain represented by dB is given by this formula. So here in these expressions, we have used the fact that voltage and current gains can be negative, but the logarithm of a negative number is not defined. So we take the magnitude of the voltage and current gain before converting them into dBs. Furthermore, power gain is always positive, no matter what. So we don't need to take the magnitude. However, care must be taken, because for voltage gain, we multiply the log with p factor of 20, whereas for power gain, we multiply with a p factor of 10, because this current here, for example, in the numerator can be expressed in terms of V naught. Similarly, this current here in the denominator can be expressed in terms of V in. So we'll have a ratio of voltage square. So that power 2 can be taken outside, and this 10 will become a 20 again. Similarly, V naught can be expressed in terms of I naught, and V in can be expressed in terms of IN, so that we again have a ratio of this time square of current value. So that square power can be taken outside again, and this will become 20. So which is why we put a p factor of 10 here when representing the power gain like this. So that brings us to the end of the first lecture. Thank you very much for your time, and we'll see you in the next lecture.